Welcome back to the Deep Dive. Today, we're taking a close look at one of the most exciting promises in the world of large language models, pushing them to truly reason.
You mean like solving complex problems, math, coding, that sort of thing?
Exactly, going beyond just, sophisticated pattern matching. And there's been significant buzz around how reinforcement learning with verifiable rewards, or RLVR, seems to be unlocking these capabilities.
Right. The idea that it could lead to models that continuously improve themselves.
Yeah, and specifically RLVR in this context.
Yeah,
It uses automated checks, right?
that's right. The core idea behind RLVR for these tasks is using automated checks. Did the math answer get verified as correct? Does the generated code pass the unit tests as the direct signal for training?
So it gives this objective feedback.
Precisely. And it doesn't require expensive human annotation of reasoning steps, which is a huge bottleneck.
And the hope, I guess, was that by rewarding these verifiable successes, especially on really tough problems.
The models would be incentivized to develop more advanced internal reasoning processes.
Like what kind of processes?
Well, think about exploring different solution paths, maybe catching their own errors, refining their approach iteratively, um, behaviors we associate with deep reasoning.
Okay. And we've seen models like OpenAI O1 and DeepSeek R1 mentioned.
Yeah, they've been cited as examples demonstrating pretty impressive performance gains on hard benchmarks, seemingly validating this whole approach.
But, and there's always a but in research, our source material for this deep dive asks a really critical question.
Which is,
RLVR truly creating new reasoning capacities in these models? Or is it primarily impacting something else?
okay. So we're diving into a specific research paper.
We are. It's titled, Does Reinforcement Learning Really Incentivize Reasoning Capacity in LLMs Beyond the Base Model?
Interesting title. Who's it by?
This paper comes from Leap Lab at Tsinghua University and Shanghai Jiao Tong University, and they provide a really rigorous technical reexamination of RLVR.
And they found something surprising.
They introduce some, quite surprising findings that challenge the sort of conventional narrative around RLVR and reasoning.
Okay.
So our mission today is to unpack the key technical insights from this paper. We want to understand exactly what their analysis reveals about the mechanism of RLVR's impact.
And get a clear, informed picture of what this means for the future of training reasoning in LLMs.
Exactly. And just to be clear, we're focusing strictly on the technical details and implications presented within this specific research.
Got it. So let's start by setting the stage properly. What exactly is RLVR in this context, and why was it seen as such a potentially powerful tool for reasoning?
Okay. So at its heart, RLVR for tasks like math or coding. It means using reinforcement learning, where the reward signal is basically a binary check.
Binary, like yes or no.
Yeah, either the final output, the math answer, the code execution is correct and verified, or it's not. You get a positive reward for correctness, zero otherwise. Simple as that.
And that automated verification, that's the key advantage, right?
It seems like it.
Because, traditional RL might need complex state stuff or carefully designed reward functions. And for language, especially reasoning, getting detailed human feedback on why a reasoning path is good or bad, that's incredibly expensive, hard to scale.
Right. You can't just have humans label millions of math solutions.
Exactly. RLVR just bypasses all that by checking the end result. Did you get the right number? Did the code run without errors and pass the tests? That's your reward signal.
Yeah, it makes training on massive data sets of problems actually feasible. And the intuition, I suppose, was if you reward the model for solving harder and harder problems.
It would naturally figure out more sophisticated ways to reason. It'd be encouraged to explore more complex chains of thought, maybe backtrack and try again if it hits a dead end.
Basically learning to think more effectively to maximize those verifiable rewards.
Precisely. The belief was that RLVR could push models beyond the capabilities they got from just pre-training, that it could unlock these advanced behaviors.
Like what specifically?
Things like deep enumeration of possibilities, self-reflection on intermediate steps, maybe iterative refinement of solutions, stuff the base models didn't seem to do reliably on their own.
So it was seen as a path towards models that could become genuinely better at reasoning over time.
Maybe even discovering novel problem-solving strategies. That was the dream, anyway.
Okay, that was the exciting promise. But the paper immediately flags a potential issue, and it's with how we were measuring this improvement.
The metrics, right. The common way to measure performance has been using things like pass at one. Pass at one tells you the percentage of problems the model solves on the first try, given just one attempt to generate a solution. Or maybe you look at the average performance over a few samples, like pass at 5 or pass at 10.
But the researchers here argue that pass at 1 or average performance
Mm.
doesn't really tell you the whole story.
Not about the model's ultimate potential, no, or the boundary of problems it could solve given enough chances.
Right. Like, think about a human solving a really tough math problem.
You probably wouldn't get it right on the first attempt.
Exactly. You might try a few different approaches, explore different avenues, maybe make a mistake, backtrack, try again, until you find the correct solution path.
And a model could potentially do the same thing. If you only look at its first attempt, you might think, nope, can't solve it.
When actually, if you just gave it more attempts, it might eventually succeed.
So, to truly measure that deeper capacity, the paper introduces a different metric as their main tool.
Which is pass at K. How does that work?
So, pass at K, it measures the percentage of problems where at least 1 out of K independently generated samples is correct.
Okay, so instead of just one shot, you generate K, different possible solutions or reasoning paths for each problem.
Right. And if any single one of those K attempts leads to the correct verifiable answer, then you count the problem as solved for that specific value of K.
I see. So by using a large value for K, say K100 or maybe K200,
You're essentially giving the model hundreds of chances to find a successful reasoning path for that problem.
it lets you probe the boundary of what the model is capable of solving.
Exactly. It reveals the extent of problems for which the model possesses at least one valid reasoning trajectory within its, probabilistic output distribution.
Even if that path is maybe low probability and needs multiple samples to actually find it.
Precisely. It's a measure of the model's potential reach or coverage for reasoning, not just how efficiently it finds a solution on the first try.
Okay, that makes sense. They also mentioned using an unbiased estimation method for pass at K. Why is that important? Is it just faster?
Well, yeah, calculating pass at K directly by actually generating K samples can be super computationally expensive, especially if K is large, like 256 or more.
Right, doing that for thousands of problems across multiple models.
It adds up. So the method they use, which is adapted from some prior work in code generation, lets them generate a smaller number of samples. Let's call it N.
Where N might be much less than K.
Right. Maybe N is 32 or 64, even if you want to estimate pass at 256. But from those N samples, they can get an accurate, statistically unbiased estimate of what the pass at K would have been if they had generated all K samples.
Ah, clever. So it makes evaluating pass at K for large values actually feasible.
Yeah, across many problems and models, it's crucial for their analysis.
Okay, so they have this robust way to measure the potential boundary of reasoning capacity, not just the efficiency. But what about that nagging concern, especially in math?
You mean models just getting lucky, getting the right final answer by chance, even if the steps are totally wrong?
Exactly.
Yeah.
How do they make sure that pass at K, especially at large K, is really reflecting genuine reasoning ability, not just, random guessing hitting the mark eventually?
That's a really important point, and they do address it directly. For math problems, which are, as you said, particularly prone to this hacking or guessing issue, they took two main steps.
Okay, what's the first?
First, they tried to filter out problems where the correct answer could be easily guessed without a proper reasoning path. Problems where just sampling numbers or simple operations might coincidentally land on the right answer.
Makes sense. Try to remove the easy targets for guessing, and for the harder problems that remained.
For a subset of the really difficult problems where the model did achieve a correct answer, maybe only at high K, they performed manual validation.
Manual validation of?
Of the chain of thought, the COTI. The step-by-step reasoning the model generated leading to the answer. They had humans actually check if the steps themselves were logically valid, not just if the final number was right.
Ah, okay. So they're confirming that when a model gets the right answer on a hard problem, especially one it only solved after many tries, high K.
It's often because it actually sampled a valid sequence of logical steps somewhere in those attempts.
That's crucial.
It is. And this manual validation, which they detail in the paper's appendix, confirmed that even for hard problems from benchmarks like GSM-8K or AME, where the base model only succeeded at large K, the majority of those successes came from samples containing at least one logically sound reasoning path.
So that strongly supports using pass at K at large K as a measure of the model's ability to find a correct reasoning trajectory.
Exactly. It suggests the underlying capability was present, it just needed to be found. It wasn't just luck or guessing the final number.
All right, armed with this robust metric, let's get into the paper's core technical findings. And finding number one. It's genuinely surprising. RLVR models, despite looking great at pass at 1, are actually worse than the base models at large K.
This is really the central counterintuitive result. It directly challenges that idea that RLVR is pushing the reasoning boundary outward.
This wasn't just on one task.
No, they show this pattern consistently. Across diverse reasoning tasks, math, code generation, even some visual reasoning, and across different underlying LLM families and sizes, it seems quite general.
So just to be clear, at small k, like pass at 1,
The RL trained models do outperform the base models, often significantly. This matches what previous work reported, and it's why these RL models were seen as state-of-the-art for certain tasks. They're definitely more efficient at getting the right answer on the first try.
Okay, so they're faster out of the gate.
Yeah.
But the twist happens when you increase k.
Exactly. As you give the models more samples, letting K grow, say, up to K128 or K256, the base models consistently catch up. And then they actually surpass the RL-trained models in terms of pass at K.
So if you plotted performance against k.
The base model's curve would climb much more steeply. It keeps finding solutions to new problems as you give it more chances. The RL model's curve tends to flatten out earlier, and importantly, at a lower final level.
Wow. Can you give us a specific example of this gap?
Sure. The paper highlights results on benchmarks like Minerva, which is a pretty challenging math data set. For one of their 32 billion parameter models, the base version was around 9% better at pass at 128 compared to the RL-trained version.
9% better after 128 tries. That's substantial.
It is. And another really compelling example they show is using a model called OAT0 on AME24. That's a very hard math competition data set. The RL versions started way higher at pass at almost 30 percentage points better, confirming its efficiency boost.
Okay, huge initial advantage.
But as K increased, the base model's performance climbed much, much faster. And eventually, at large K, the base model's pass at K actually surpassed the RL models.
It's a dramatic reversal. So what does this fundamentally suggest?
It suggests the base models already possess the underlying ability to solve many of these difficult problems. They just don't sample the correct reasoning paths as frequently or as efficiently as the RL models do on the first try.
The capability was latent, sort of hidden. It just required more exploration, more sampling to uncover.
That seems to be the implication. And remember that manual COTI validation we talked about?
Yeah, checking the reasoning steps.
The paper actually shows figures in the appendix of base models generating long, complex, and valid reasoning paths, even on the hardest problems they looked at, from GSM-8K and AME24.
These weren't just simple, short steps.
No, some were quite long,
Yeah.
involved numeration, checking conditions, even exhibiting behaviors that looked a bit like reflection. Things previously thought to be hallmarks of RL-trained models.
Okay, so finding one fundamentally shifts the perspective. RLVR isn't necessarily giving models new powers.
It looks more like it's making them more efficient at accessing the powers they already had, maybe buried deep down.
Which leads directly into finding number 2. RLVR boosts sampling efficiency, but it seems to reduce the overall reasoning scope.
Right. This finding tries to get at the mechanism behind finding number 1. Why does the RL model get better at low K but then fall behind at high K compared to the base model?
And how did they investigate this mechanism? What was the technique?
They used perplexity analysis. As you know, perplexity is a measure of how well a language model predicts a sequence of tokens.
Lower perplexity means the model thinks that sequence is more likely, more natural according to its learned distribution.
Exactly. So what they did was they generated sets of reasoning responses using 3 different types of models.
Which were?
The base model itself, the RL-trained model, derived from that same base model, and also a strong, high-performing teacher model like OpenAI O1, just for comparison.
Okay, so they have outputs from base, RL, and teacher. Then what?
Then they took all these generated responses, the chains of thought, the solutions, and they evaluated how likely each response was according to the original base model's probability distribution. They calculated the base model's perplexity for each response.
Ah, I see. So they're asking, from the base model's point of view, how surprising are the answers generated by the RL model or the teacher model compared to its own answers?
Precisely. And what they found was quite revealing, especially about the RL model.
What do they find?
The distribution of perplexities for the responses generated by the RL model when evaluated by the base model was heavily concentrated in the lower perplexity range.
Lower perplexity means more likely.
Yes. It means the successful reasoning paths found by the RL model were sequences that the original base model already considered relatively likely or probable within its own output distribution. They weren't statistically weird or surprising from the base model's perspective.
Okay, let me make sure I've got this. The reasoning paths the RL model uses to get correct answers, they aren't brand new alien patterns that the base model couldn't imagine.
That's what the perplexity analysis strongly suggests.
They are already relatively probable sequences within the base model's existing repertoire.
Exactly. That's the key technical takeaway here. It argues against the idea that RLVR is discovering genuinely novel reasoning strategies. Instead, it seems to be reinforcing successful paths that already existed, perhaps with lower initial probability, within the vast space of things the base model could generate.
So RLVR isn't really exploring uncharted territory. It's just making the model much, much better at finding the good paths in the territory it already knows.
That nails it. The RL training process, by rewarding those successful outcomes, works by updating the model's parameters to increase the probability of sampling these already existing high-reward sequences.
Which is why the RL models are so much more efficient to pass at 1 and low K.
Right. They've essentially biased their output distribution to make those known successful paths much more likely to pop up early in the sampling process. It's a boost in sampling efficiency for capabilities the base model already had, at least latently.
Okay, that explains the pass at 1 advantage. But then, where does the reduction in scope at high K come from? Why do they fall behind later?
Well, the paper argues this efficiency gain comes at a cost, and the cost is reduced exploration.
How so?
Standard RL algorithms, particularly the policy gradient methods like PPO that are often used here, they tend to reduce the entropy or the randomness of the model's output distribution as they converge on a policy.
Because they're reinforcing specific paths.
Exactly. By strongly reinforcing a subset of paths that lead to success, the model becomes less likely to generate sequences that deviate significantly from those reinforced paths. It becomes more focused, maybe more deterministic.
So it gets really good at traversing these few known successful routes.
But it becomes less likely to explore other, potentially valid but maybe less common routes. Routes that the original base model, with its higher entropy, could have stumbled upon with enough random sampling.
It narrows the search space it's willing to explore.
That's the argument. The RL process makes the model more focused on a specific set of high-reward sequences, and in doing so, it reduces its capacity to explore the broader range of possible outputs where solutions to other difficult problems might lie.
And that's why its pass at K, at large, K ultimately falls below the base model's potential.
Right. It has effectively pruned away the ability to sample some successful paths that the base model, with its wider exploration, could still find if you just gave it enough tries. The base model retains a broader coverage, even if it's less efficient initially.
This paints a really clear picture then. RLVR, as currently applied, seems to be a powerful tool for optimizing the efficiency of accessing existing reasoning capabilities.
Capabilities already present within the base model's repertoire?
But it doesn't seem to expand that repertoire. And in fact, it might actually sacrifice some breadth of exploration in the process.
That seems to be the core finding. And that leads us neatly into finding number 3, which examines the various RL algorithms themselves.
What did they find there? Are some algorithms better than others at avoiding this trade-off?
Well, the conclusion was that they show pretty similar limitations, and perhaps more importantly, they are all quite far from achieving what you might call optimal efficiency.
And optimal efficiency here means what exactly?
Making the pass at 1 performance match the base model's maximum potential, which they estimate using pass at K, at a large K, like K256.
So ideally, the RL model should solve on the first try, pass at 1, all the problems that the base model could solve given hundreds of tries, pass at 256.
Exactly. That would be perfect sampling efficiency. To quantify how far current methods are from this ideal, they introduced a metric called the sampling efficiency gap, or SE.
How's it calculated?
Simple subtraction. It's the pass at 1 performance of the RL model minus the pass at K256 performance of the base model.
Okay. And a large ARS means?
A large ARS indicates the RL algorithm is still falling significantly short. It's not managing to make the most probable output, pass at 1, cover the full potential scope, pass at 256 that the base model inherently possesses. A lower A would be better.
And they tested various popular RL algorithms using this metric.
Yes, they conducted controlled experiments. They used a framework called VREL and some specialized mathematical data sets called OmniMath, which had both in-domain problems, similar to training, and out-of-domain problems, more challenging transfer.
Which algorithms did they compare?
They looked at a range. PPO, which is very common, GRPO, reinforced plus RLO, Remax, and DPO. A decent selection of recent methods.
And what was the result? Did one stand out?
The results were remarkably consistent across the board. While there were some slight variations in the exact pass at 1 and pass at 256 numbers between algorithms.
The overall picture was the same.
Pretty much. The sampling efficiency gap, AT, was large and consistent across all the tested methods. For the in-domain test set, for example, the AT was consistently above 40 percentage points.
40 points, that's a huge gap.
It is. It means none of these RL algorithms were getting close to unlocking the base model's full potential with just one sample.
So whether it was PPO or RLOO or DPO, none of the current methods seem to fundamentally change that core dynamic we discussed. The efficiency boost comes with a scope limitation.
Exactly. It suggests the limitation might be more fundamental to the current approach of using RL with sparse end-task rewards in this kind of vast pre-trained space, rather than just being a deficiency of one specific algorithm.
Did they note any minor differences between them?
They did mention a few nuances. DAPO, for instance, had a slightly higher pass at 1, but it was also more computationally expensive, and actually had slightly worse pass at K at the high end. RLOO and Reinforce++ seem to offer a reasonable balance between effectiveness and efficiency. Remax performed a bit less well, possibly due to issues with how it estimates the reward baseline.
What the main message is.
The main takeaway is that the gap between current RL efficiency, pass at 1, and the base model's latent potential, pass at 256, is substantial, regardless of the specific algorithm used from this common set. They're all operating under similar constraints.
Okay. This really begs the question then. If RLVR isn't creating new reasoning abilities, is there any training paradigm discussed in this paper that is shown to actually expand the reasoning boundary, to go beyond the base model?
Yes. That brings us to finding number 4, which provides a really important contrast by looking at a different technique. Distillation.
Distillation.
Yeah.
Now, in this context, that usually means training a smaller student model to mimic the behavior of a larger, more powerful teacher model.
Correct. And specifically here, it involves training a model not just on final answers, but on detailed data generated by a stronger teacher model. Things like the step-by-step chain of thought traces that the teacher used to arrive at the solution.
So it's more like learning by observing and replicating a master's process, not just copying their final answers.
Exactly. It's akin to instruction tuning, but with much richer, detailed reasoning examples from a model that's already known to be better at reasoning.
Okay, and how did a model trained via this kind of distillation compare in their pass at K-analysis?
This is where things get really interesting. The paper presents a comparison showing the pass at K curves for several models. The base model, a standard instruction tuned model, an RL trained model, and model trained via distillation.
And the distilled model.
The distilled model's pass at K curve was different. It wasn't just higher than the RL model's curve, it was consistently and significantly above the original base model's curve, across all values of K, from K1 all the way up to K256.
Wow. Okay, so unlike RL, which seemed to be bounded by the base model's capacity and mostly just improved efficiency within that boundary,
distillation did seem to genuinely expand the set of problems the model could solve, even when given many, many chances at large K.
it pushed the boundary outwards.
That's the strong conclusion from this finding, yes. Distillation, by transferring knowledge and specific reasoning patterns from a stronger model that already possesses more advanced capabilities, can introduce genuinely new reasoning abilities or significantly expand the student model's solvable problem set beyond what its original base architecture was capable of achieving alone.
So distillation is fundamentally about learning new tricks from a better source.
Right. Whereas current RLVR, applied directly to a base model, appears to be more about getting faster and more reliable at performing the tricks that the base model, deep down, already mostly knew how to do.
That's a really clear and important distinction highlighted by this paper.
It definitely shapes how we might think about combining these techniques or choosing between them.
Let's maybe dig into some of the finer analysis points that solidify these findings. You mentioned they provided concrete examples regarding the solvable problem sets.
Yes, exactly. The paper includes Table 4 and Table 5, if you're looking at it, that list specific problem indices from benchmarks like AMU24 and LiveCodeBench.
And what do these tables show?
They show which specific problems were solved by the base model at K256 versus which were solved by the RL train model, also at K256, although its peak might be lower. And what these tables illustrate quite clearly is that the set of problems solved by the RL model is very largely contained within the set of problems solvable by the base model.
So the RL model solves a subset of what the base model can eventually solve.
Predominantly, yes, it reinforces that idea. The RL model isn't cracking fundamentally new types of problems that the base model was completely incapable of. It's just becoming more efficient at solving a specific high-reward subset of the problems the base model could potentially handle, given enough exploration.
It's increasing the overlap with the hard-to-reach problems within the base model's potential set, maybe.
That's a good way to put it, but it's not really venturing into entirely new territory, problem-wise, that the base model couldn't touch at all.
Okay. What about the effect of training time? Does just pushing the RL training for more and more steps eventually break through this limitation? Or does it, I don't know, make it worse?
That's another critical aspect. They examined the asymptotic effects of training. They used their controlled setup with the VRL framework and OmniMath datasets.
And they tracked performance as they just kept training the RL model for more steps.
Exactly. They looked at how metrics like PASSET-1 and PASSET-256 evolved over hundreds of training steps.
And what did they see happening?
Well, for PASSET-1 on the training set, performance generally continued to improve with more steps, as you might expect. The model got better at the problems it was explicitly trained on.
But on the test sets, the unseen problems.
On the test sets, both the in-domain one and the harder out-of-domain one, the PASSET-1 performance tended to plateau after a certain number of training steps, maybe around 150 to 300 steps in their experiments. Further training didn't really boost PASSET-1 much more on unseen data.
Suggesting some overfitting, maybe?
Likely, yes. But the really crucial finding was what happened to PASSET-K at large K, specifically PASSET-256, as training continued beyond that PASSET-1 plateau.
What happened to the boundary measure?
It actually started to decrease. As they increased the RL training steps further, the model's PASSET-256 performance on the test sets got worse.
Worse. So prolonged RL training, instead of maybe eventually pushing the reasoning boundary outwards, actually caused it to shrink.
That's precisely what their data suggests. The model's ability to solve problems when given many chances actively deteriorated with excessive RL training.
Why would that happen?
The likely reason, tying back to our earlier discussion, is the continued reduction in the model's output entropy and exploration capacity. As the RL objective keeps converging, the model becomes overly specialized or focused on the patterns seen in the training data.
It gets too good at the training problems.
Right. It becomes very efficient at solving those, but it loses the ability to explore the diverse reasoning paths needed for the broader set of test problems, especially the ones that required multiple samples, high K, to find a solution in the first place. Overfitting meets reduced exploration.
That's a pretty damning finding for the idea of just train RL longer to get better reasoning.
It certainly suggests diminishing returns and potentially negative returns on reasoning scope with prolonged training using current methods.
They also briefly touched on the effect of sampling temperature during evaluation, right? Did that change the picture?
They did look at that. They varied the temperature used when generating the K samples for the PASSET-K evaluation. They found that the base model's performance tends to drop off significantly at very high temperatures, like T1.0.
Why would that be?
Probably because the increased randomness at high temperatures makes the generated sequences less coherent, less logically structured, and just more random babble.
And the RL model?
The RL model, because its output distribution already has lower entropy due to the training, was found to be more stable and less negatively affected by high temperatures. It's already more focused.
So why did they choose the temperature they used for the main results?
They noted they chose a temperature of T0.6 for their main experiments. They argued this was a sweet spot that allowed both the base model and the RL model to perform well, showing their characteristic differences in the PASSET-K curves clearly, without either model being unfairly penalized by a temperature that was too high or too low for it.
Okay, that makes sense. So all this provides a lot of detailed evidence supporting their core findings. RLVR improves efficiency but shrinks scope. The algorithms tested share this limitation. Distillation is fundamentally different.
Yeah.
Let's try and bring this back to the bigger picture now. Why do these findings really matter? What are the broader implications?
Well, the paper argues these findings point to some pretty fundamental differences between applying RL to fine-tune these huge pre-trained language models for reasoning and the classic success stories of RL in other domains.
Like game playing, AlphaGo, Atari, that kind of thing.
Exactly. In those domains, RL agents often seem capable of achieving almost unbounded self-improvement, discovering truly novel strategies. The paper asks, why doesn't that seem to be happening here with RLVR for LLM reasoning?
And what are the key differences they point to?
They highlight two major ones. First is just the sheer scale and nature of the action space.
Meaning?
Generating a sequence of tokens, like a math proof or code, is a vastly larger and more complex combinatorial search problem than choosing, say, the next move on a Go board or a button press in an Atari game. The space of possible sequences is just astronomically larger.
Okay, that's one difference. What's the second?
The second key difference is that LLMs don't start from a blank slate. They start with an incredibly powerful, complex, and often quite rigid pre-trained prior that's learned from ingesting massive amounts of text data during pre-training.
Whereas traditional RL agents often start from scratch or with much simpler, maybe random initial priors.
Right. And this powerful pre-trained prior in LLMs acts as a kind of double-edged sword, according to the paper's hypothesis.
How so? What's the good edge and what's the bad edge?
Okay, the good edge is crucial. In that absolutely enormous language action space, the pre-trained prior gives the model a massive head start. It already knows how to generate basically coherent text, follow general instructions, understand concepts related to the problem.
It guides the exploration.
Massively. It makes it even possible for the RL process to find any successful reasoning paths that lead to those sparse positive rewards. Without that prior guidance, exploration would be essentially random noise in an infinite space, and it would almost certainly fail to find anything useful.
Okay, so the prior is essential to make RL tractable at all. What's the downside? How does it constrain the RL process?
This is the core of their hypothesis. The training process used in RAVR, especially with policy gradient methods like TPO, typically involves a mechanism to keep the learned policy close to the original policy. Often there's a penalty, like a KL divergence penalty, for deviating too far from the base model's distribution.
Why is that penalty there?
It's usually necessary for stable learning. It prevents the model from suddenly changing its behavior drastically and collapsing during training, especially in such a huge action space.
But the paper argues this stability mechanism also acts as a constraint.
Exactly. By penalizing deviations from the original policy, the base model's prior distribution, it inherently discourages the model from exploring sequences or reasoning patterns that are significantly different from what the base model would typically generate.
So let's say there was a genuinely novel, maybe counterintuitive, but ultimately correct reasoning strategy out there.
If that strategy involves generating token sequences that look very weird or unlikely according to the base model's strong prior,
The RL process is likely to penalize the initial steps of exploring that path just because they deviate too much from the prior, even if it might lead to a breakthrough.
that's the crux of the argument. The RL process becomes effectively constrained to optimize primarily within the landscape defined by the base model's pre-trained distribution. It gets really good at finding the peaks, successful paths within that known landscape, but it's discouraged from venturing too far off the map to potentially discover entirely new continents of reasoning.
Which explains why the RL model's capacity seems to stay bounded by the base models and can even decrease with excessive training if it over-optimizes within that boundary.
Precisely. It reinforces sampling existing successful patterns more efficiently. But the mechanism that enables stable learning also hinders the discovery of truly novel ones that lie far outside the prior.
Wow, this really challenges that common narrative that just applying standard RL to a base LLM with verifiable rewards is the direct path to pushing the frontier of reasoning capacity itself.
It seems much more suited, based on this analysis, to refining and improving access to the potential that's already there in the base model.
Which is valuable but different from creating fundamentally new abilities.
Exactly. And that's the key implication the paper drives home. While maybe starting with a stronger base model, perhaps one already improved by, say, distillation from an even larger model, could lead to incremental gains when you apply RLVR.
The current RLVR methods themselves seem fundamentally limited in their ability to achieve that dream of continuous, unbounded self-evolution of reasoning capacity, starting from a fixed base model.
So where does this leave us? If current RLVR isn't the key to unlocking new reasoning frontiers, Where do the researchers suggest we should be looking next?
Well, they really emphasize the need for new research directions, particularly focusing on developing better exploration methods. Exploration methods, specifically designed for these huge pre-trained language spaces.
Yes. We need ways for models to effectively search for and discover rewarding sequences that might lie outside the comfortable boundaries defined by the strong pre-trained prior. And crucially, to do that without just generating incoherent nonsense, which is the risk when you stray too far from the prior.
That sounds like a really hard problem.
It absolutely is. Finding that balance between leveraging the prior for guidance and having the freedom to discover novelty is likely key.
And does it also suggest maybe exploring alternative or hybrid training paradigms?
I think that's strongly implied. Maybe combining the strengths of RL, like its ability to optimize towards a clear, verifiable goal, with methods like distillation, which can inject novel capabilities, or perhaps new forms of instruction tuning or other techniques that can genuinely expand the model's representational power or generative patterns.
So the takeaway is that pushing the actual reasoning boundary likely requires approaches that go beyond just making sampling from the existing distribution more efficient.
It seems so. Approaches that can genuinely expand the model's core capabilities or knowledge base seem necessary for the next big leaps.
Now, it's important, as always, to acknowledge that this paper exists within a larger research context. They do briefly mention related work, right?
Yes, they do. They position their work relative to recent advancements in using RL for LLM reasoning. They cite examples like models developed at DeepMind, some of the work coming out of OpenAI, DeepSeek's math model, and various open source efforts in this space. They also nod to related work in multimodal RL where similar ideas might apply,
But they frame their specific contribution
as providing a more systematic, really in-depth analysis of the specific mechanism and, importantly, the limitations of RLVR when viewed from the perspective of the base model's underlying capabilities. Using that pass at K-metric as a tool to rigorously probe the reasoning boundary is central to their contribution.
So while others might have hinted at similar things,
Right. They note that while some previous studies might have shown maybe base models exhibiting some reflective behaviors, or perhaps isolated instances where pass.k deteriorated in specific settings.
this paper provides the more comprehensive evidence and analysis across multiple benchmarks, different model families, various algorithms.
Exactly. Enough to build a stronger, more general conclusion about the fundamental behavior of current RLVR techniques in this particular domain of complex reasoning.
Got it. And finally, the paper includes just a very brief note on broader impacts.
Yes, just a standard brief mention. They essentially say that potential negative social impacts are generally aligned with the broader implications of any advanced LLM reasoning technology. And they just underscore the importance of adhering to principles of fair and safe deployment for these kinds of powerful systems. Nothing too specific beyond that.
Okay, so wrapping things up from this deep dive,
Yeah.
it's definitely provided a much more nuanced and I'd say technically grounded understanding of what RLVR is actually doing for LLM reasoning, at least based on the evidence in this specific paper.
Yeah, the key takeaway seems to be that while current RLVR methods are really effective at improving sampling efficiency, making models better at finding correct answers quickly, boosting metrics like pass at 1,
They don't appear to be creating fundamentally new reasoning capabilities beyond those that were already latent or hidden within the base model to begin with.
and this efficiency gain seems to come with a trade-off. It reduces the model's overall reasoning scope or coverage when you give it many chances, as measured by pass at k at large K.
We also saw that the current RL algorithms they tested largely share this limitation. None of them seem close to making the model's first guess achieve the full potential reach of the base model.
And critically, the contrast with distillation was stark. Training via distillation from a stronger teacher can genuinely expand the model's reasoning boundary and introduce capabilities beyond the base model.
Which really highlights that distillation and RLVR in their current forms seem to be doing fundamentally different things to the model. So these findings are pretty significant because they challenge that maybe overly optimistic view that simply applying RLVR to a powerful base model is the magic bullet for unlocking continuously self-evolving superhuman reasoning.
It suggests the path forward might be more complex. It points towards needing new approaches, maybe better exploration techniques, maybe hybrid methods that can actually overcome the constraints imposed by that powerful but limiting pre-trained prior, especially in this vast language space.
This really raises a fundamental question for me, thinking about this. If current RLVR is primarily optimizing access to existing capabilities rather than creating new ones, What does that imply about the richness and nature of the abilities learned during that massive, unsupervised pre-training phase?
That's a great point. It suggests there might be a huge amount of latent potential already baked into these base models.
Right. And if that potential is already in the base model, just waiting to be unlocked by, say, enough sampling, how do we design better training methods? Methods that can effectively explore and harness that full latent capacity, perhaps without being quite so constrained by the very prior that makes the initial exploration possible.
That feels like the million-dollar question, doesn't it? How do you best leverage the prior without being trapped by it?
Exactly. Definitely a lot to consider as the field moves forward.
Absolutely. Food for thought.
Indeed. Well, that brings us to the end of this deep dive. Thanks for joining us.